K-E-R-B-A-C-K-E-R at uidaho.edu. You may email him with questions, and then that's one way of getting your questions addressed here tonight. And of course, all of you here only have to raise your hands for your questions and comments. So I'm Ken Baker with Better Bricks Education and Training, and on behalf of Better Bricks and our sponsors, the Integrated Design Labs in Idaho, U of I Integrated Design Lab, Bozeman Integrated Design Lab, Northwestern Energy out of Montana, Idaho Power right here, and the IURDC, Sherry McKibben sitting right here, and USGBC chapter, Idaho chapter. All of our sponsors for this, thank you, thank them. And again, thank you for being here. We have a good topic tonight, implications of the 2030 challenge, and we have my friend and colleague Terry Egner, and a very good presenter, understands this information very well, that will be presenting tonight. I wanted to say before we get too deep into this, though, our next session on our flyer says Wednesday, October 28th, and that was David Goldberg to talk about low-tech architecture, load reduction, and passive strategies in the Northwest. That's been rescheduled. That's been rescheduled to December 10th, and we'll send out word again on that, but that's been rescheduled to December 10th, which is a Thursday. So we'll still have that presentation, but it's been rescheduled, and that actually, we'll have a November presentation previous to that. That's on your flyer. And again, I'll send out information on that for those that don't have the flyer. With that, I think we should get going into the session here. Terry's got, he has a lot of slides and a lot of information he wants to give us, so I don't want to cut him short. But I will. If he starts going overtime, right, Terry? He knows me pretty well.
You know me pretty well.
Yeah, yeah. Terry's very passionate about this information, and this implication of the 2030 challenge that he's going to talk about tonight is, I think, one of the more timely, better presentations that I have seen for a while, because we're talking about 2030 challenge and what that does mean for us, but what it means from the standpoint of where we have to get to as far as carbon emissions in our buildings. So Terry's going to tell us all about that. Terry Egner, microgrid. He has his own business, although he's semi-retired, less retired than he used to be, I think, or than he ever was, probably. I think I'll leave it at that. If you want to say anything more about yourself, He's been working in this field for longer than most of us out here.
More than I want to admit, I suspect. Well, thank you all for being here. Just quickly, how many architects? Engineers? Building facilities managers? Students? Great, nice mix. I always like to know who's out on parole, so way of figuring it out. Better Bricks, I'm going to skim past this since Ken's already mentioned it, except to point out, as you see on the screen here, be sure to make sure that you get to the Better Bricks website, because it's an excellent source for information. It's an excellent source for case studies. They normally have cutting edge information, as well as ways to get to information that you may want about, for instance, tools or background on a particular topic. So, betterbricks.com, it's easy to remember. Should be on your list, should be on your favorites. Today we're going to be talking about the implications of the 2030 challenge, and particularly net zero as an issue, which of course is the ultimate goal. Now, I want to say right up front, there are about as many definitions of net zero as there are people writing in this field. Everybody has their own opinion as to exactly what's in and out of the mix. However, I do want to point out that the 2030 challenge, as we'll be talking about in a couple of minutes, is based really on carbon, not on energy. And as such, when I talk about net zero in this presentation, I am going to be talking about the carbon impact based on site energy only. Okay, site energy only. So I am not bringing in the multiplier for electricity depending on its source, because I have no way of knowing that. Okay. If the other thing to keep in mind about this controversy, in some ways it's a tempest in a teapot, in that if you know one of the numbers, you can always get the other. That is to say, if you're working from site energy, you can get to source energy. If you want carbon, you can get carbon at site and carbon source. Those are numbers that can all be worked out. So as long as people are clear about what they're using, I don't think that there's really as much controversy as one would suspect. What we're going to do is I'm going to give you an introduction, or probably for most of you a review. Then we're going to look at what the numbers really look like. Then go on to the market challenge that getting to net zero represents for this country. Some of the technical issues involved, and then some potential solutions. At any point during this, feel free to chime in with a question, a comment, a challenge, an insult, doesn't matter. Take it where it needs to go, because we're all at the front end of this process. There are multiple drivers right now. Some of these aren't, for instance, the energy cost issue is muted these days relative to where it was 2 years ago for two reasons. One, costs have come down, and number two, nobody has any money to spend on energy, and so they don't notice it as much because we're driving a lot less, because we're working a lot less. However, energy cost still remains an issue, and anybody that thinks it's going to go down long haul over the long term, I think, is wishful thinking. The second general issue is sustainability, which I represent with a landfill here, which is the reverse of sustainability. But that has become a major topic worldwide, and it is, in fact, a major driver, even though it's not specifically energy. And then finally, climate change, which is, of course, the central driver for the 2030 challenge. And I think pretty much the people who are, you can tell by the way they're defined now, the deniers of climate change are rapidly retreating, because the evidence is so compelling. Now, that doesn't mean that we all know what's causing it, what the implications are, what the changes will be. What is clear is it's going on. That's all that's clear. The rest of those issues still are very much up in the air. Having a little, I'm not used to working with a mouse as a pointer, but since we have participants who are watching on the screen rather than here in the auditorium, I have to be careful when I point to use the mouse instead of a pointer or my finger. I apologize if I screw it up here. Okay, you're all familiar with this. This litany has been pretty much around for a number of years now. The most important number from the standpoint of the 2030 challenge is this one. This one right here, 39% of total US CO2 emissions, because there's no doubt that CO2 is one of the prime drivers to climate change at this point. And so that's what drove actually the discussion around the 2030 challenge, or the development of it. Ed Mazaria, who is an architect and engineer, spearheaded a development of this concept and worked to bring the scientists in who could explain what the real options were and what kind of timeline we really had. And out of that grew the 2030 challenge itself, which has become widely adopted, supported ASHRAE, AIA, New Buildings Institute, EPA. Pretty much everybody has come on board as a viable way to look at the problem. There are three elements to the 2030 challenge, essentially. when all the dust settles, not counting the educational questions that Mazria has raised about curriculum development in schools of architecture. But in terms of the impact on buildings, there are three elements. One is we should reduce fossil fuels immediately, and this was when it first came out a number of years ago. So we should be doing buildings at half of what? 50% of what? Anyone know? 50% of the average building. And the average building was defined by the Commercial Building Energy Study, is it? Survey. Commercial Building Energy Survey, CBEX. I'm so used to calling it CBEX, I've forgotten what it means. Which is a study that's done by the government on a regular basis, and it basically has laid out this is the typical usage. So 50% below that, 50% better than the average building. At the same time, we need to do the same thing with an equal number of renovated buildings, of existing buildings that are being renovated. Now that isn't quite as complex as it sounds, because it turns out that the number of new buildings built in a given year, which is about 2% of our building stock, is also the number of buildings that are renovated every year, which is about another 2% of our building stock. Those numbers are actually quite comparable. Not exact, but close. Then, of course, he throws in the ringer and increase the savings target by 10% every 5 years starting in 2010. So what we're looking at is next year, actually more accurately January 1st, a couple months from now, we will go from 50% to 60% savings is what we should be doing if we're going to meet the carbon targets that we have set, the carbon offsets. Okay, so we now have 50, 60, 70, 80 as we go down through the 5-year periods between now and 2030. Ultimately ending up with net zero. Now, I need to be clear that the savings don't have to be reductions. They can be offsets if they're offset by a truly carbon neutral fuel source. That is to say, like photovoltaics, wind, whatever. So net zero means that the building still can use energy, but it has to be using renewable energy, not carbon-based energy. Okay, what's 50% of the average building look like as a number? Okay, here's the first problem we run into, and that is nobody knows what these numbers are. And you people are professionals. And if you don't know them, you can be sure that the person on the street is even more clueless on this issue. So what we're going to do is we're going to start out with some numbers. If I said to you a car got 40 miles to a gallon, good or bad or average? Thumbs up, thumbs down. Put your thumbs up. Let's see it. What does everybody think? Okay, everybody knows that. Isn't that interesting? You all know how many miles per gallon. Okay, how about if I say 12? Thumbs down. What if I say 30? No, there's a couple of hard-nosed people here who think 30 is not good enough. Yeah, okay. But generally it's medium to up. It's certainly average. I mean, average in the sense of typical. You wouldn't have to go to an extreme to get there. You wouldn't have to buy one of the 2 or 3 models out there that will get better. Okay, so we're going to look at some numbers. These are the numbers. And there'll be a quiz on these at the end, so you better stare really hard. Okay? These are the numbers in kilobTUs per square foot per year. KilobTUs per square foot per year. Now, those are equivalent in energy terms to miles per gallon. That is to say, this is how much energy you would have per square foot. Now, why per square foot? Because building sizes vary, right? But, and by the way, this slideshow is going to be available email, right? As a...
This will be archived.
Archived, anyway.
The IDEO website.
So if we're talking about less, 50% less, we're talking about 42,000 BTUs per square foot per year. That would be an average building. half of an average building, I'm sorry, 50% less than an average building. And as you go on down to 0, you can see the numbers get smaller and smaller. Okay, so when we're looking at these numbers, I want you to keep them in mind because they're basically going to give us some idea of how steep the challenge is when we start to deal with them. Right now, here's CBEX, and what I've got, pointing, sorry. Here's CBEX up here. CBEX average is this red spot. It's about 84,000 BTUs per square foot per year. That would be a typical building. And this is based on the 99 CBEX standard. By the way, they've done another one since then, which is 2003, I believe, is the one that's complete. And that has gone up to about 92. So even though we've gotten smarter and a lot of energy efficiency work's been done, the average building's using more. Why? Primarily electronics. We've got more computers, more printers, more copiers, more faxes. That's what's driving the increase. We've got a lot of charging units, plug-ins for our phones and our everything else. Okay, so there's the number, 84 right now. So what we're talking about is that for the 2010, we should be down here at about 42, this yellow rectangle over on the right. Okay? And then in here we've got some other things that I've thrown in, which may or may not sound familiar to you. ASHRAE 90.1, 1999, 2001, and 2004. Yes, sir?
So Terry, if you're meeting ASHRAE 90.1 2004 now, you're already at half of CBEX, is that right?
Close, that's right.
Close.
Yes.
So if you're, I mean, the way that we seem to work is we base it on percentage improvement over ASHRAE.
Right, and the problem is that ASHRAE, well, I don't know, the new ASHRAE, 2004, they started to bring in plug load, didn't they? Or that's in the appendix, I guess. The problem with ASHRAE is it doesn't quite include everything. Yeah, but you're basically, conceptually, you're on the right track. If you're following a 2004 code carefully and you're actually being tested on it, that is to say that the code officials are holding you to it, then you'd probably be close to that half number we're looking for. So one side of it is, it really is not rocket science to get to 50% because we are wasting so much energy, stupidly. So it isn't a big problem, that part. And you also see the ASHRAE Advanced Energy Design Guides, AEDG, oops, sorry. Here, those are yet below that, and they really are definitely more than 50% better, as is the New Buildings Institute AB Core Performance Guide, both of which those guides offer at least 30% better than code, better than 90.1. So right now we've got design guides out there would get us to that 50%. However, if we are going for 60% January 1st, we've got to do those things plus a little more. Because as you can see here with the breakout, 2010, 60%, now we're down to about 30. We're a little below AB Core Performance if we were to be 60% below average. Okay? And if in 2015 we're going to be 70%, et cetera. Now, this becomes particularly important when we start to look at the range of what's cost effective to deliver with renewable energy. Okay? Because one could argue, well, hey, I got an 80,000 kilobtu building. I'll just buy 80,000 kilobtus per square foot of wind. I'm off the hook. I'm all done. Well, that's fine until you start to price that. And then you discover, yeah, you're off the hook if you're a millionaire and you don't mind throwing it all away on energy. But in terms of what's cost-effective renewables for buildings, and particularly if you get into site renewable building energy, which would be primarily photovoltaics at this point or biomass, the costs are quite a bit higher. And so typically most people who look at this issue, look at net zero, they're finding that somewhere between 10 and 20 kilobTUs per square foot is what you ought to expect to be able to get for a building. So you've got to bring the building use down to 20 because you're probably not going to be able to get offsets to more than 20. So what we really are saying is that we've got to get down to about 20 using efficiency. And then from 20 on down, we can buy our way out with renewables. Because there is no point in talking about a building with no energy use, because it's probably not a productive building. It's probably, a warehouse. Okay, now, what I do want to do is ask Ken, I'm going to ask him to jump in here for a couple minutes and talk about what code's doing right now, so you get a sense of how this all floats, because what are the drivers to get there if code's not one of them? So, Ken, if you could.
Okay, I'll keep it short because I want you to talk. But I've been working on a national code change with New Buildings Institute, and Terry works for New Buildings Institute, puts together programs. But what we've come up with, based on Advanced Buildings Core Performance, which is an MBI program, is a new code, core energy code that has been submitted to the International Code Council, and this month it will be considered by that council as adoption for the 2012 codes. And that will put us somewhere right below this AB core here. This is where we are in Idaho right now, at the 2004 ASHRAE or 2006 IDCC deemed equivalent by DOE as far as efficiency for codes go. So this is where we're at. This is where we could be going by 2012, somewhere here. We could actually be going a little bit more because that core energy code is about 20, depending on, it's a big nation and there's a lot of climate zones. Depending on the climate zone and the building type, you can save more or less energy. So somewhere between maybe 20 and 30% energy savings over the 06. But there is another substantial proposal that's in that is like a guaranteed 30%. And the reason that we submitted two proposals, the first proposal, the one that's right here, right below AB Core, has a new section, new chapter section in it, 506, that says do all of these things to be efficient, just like envelope, lighting, and mechanical. Do all these things, envelope, lighting, mechanical, to be efficient, just like the code usually does. And then choose from one of these other three options to make your building even more efficient. And the other three options are more efficient mechanical systems, or lower lighting carbon densities, more efficient lighting systems, or the third one, 3% renewable for your building. So this is a proposal that's actually in there to ICC that'll be reviewed. The second proposal that's sitting there, and by the way, Department of Energy signed on to that proposal. It's there, not just in NBI's name, but Department of Energy and AIA, American Institute of Architects, worked with us, and they signed their names on that proposal too. The second proposal that gets us to 30%, again, has the sign-on, and the reason it gets us to 30% because it makes those three options on the extra efficiency for lighting or mechanical or renewable, makes those mandatory, all three of them, not a choice of one out of three. So that's basically codes, and the Waxman-Markley bill that passed the House, and I don't know where it's at in the Senate, the Waxman-Markley bill says 30% by 2012. That was one of the drivers of this code. It says by 2015, 50%, using this as a baseline, 50% better. And then every year after, every 3 years, it goes on a 3-year cycle, an additional 5% efficiency until 2030. We are at net zero. So it's out there from a code structure standpoint. I just wanted to point that out to everybody. Thanks.
That's wonderful. Thank you, Ken. So you all have a much better sense of where this is going. Codes are critical, not just as public policy, but because they represent historically, they represent the state of the art. That is to say, the way things ought to be built. And so without that, it's hard to argue with somebody that you need to go further if there's a code that's sitting, way up here somewhere in the ozone. And we're trying to get energy values that are way down here somewhere. So having the code tracking is important. The second thing is that there's this distinction between codes. Some codes are life safety issues. In fact, many codes are life safety issues. And others have to do with public policy, zoning, and those kinds of issues. What is happening here that is important is that the code officials are beginning to recognize that climate change is a life safety issue. It's not a policy issue. It's not a preference. It's a significant impact on our culture that is not potentially reversible. And therefore, it becomes an important element. We could discuss this further later on if you want, but I'd like to keep moving quickly through this next piece. We're going to talk now about, so what do you do with this? Well, if you look at the blue rectangle there, these should be squares, but that doesn't work on this format, so it's rectangles. The blue rectangle represents, I'm telling you it is, the 100,000 new buildings that are built this year. Okay, so there's 100,000 new buildings built this year. The green represents of both new and existing buildings, buildings that have gotten the Energy Star Award, which means they're 75% percentile in terms of energy use in the country. And then the light blue represents all the buildings that have signed up for LEED since its inception. And the red represents the buildings that we have been able to track down that are recognizably 50% better than ASHRAE 2001. And that black dot in the corner is all the buildings that we know of that are net zero or close to it. Okay? So you got the scale. We're looking at 100,000, about 18,000, about 4,000, I'm sorry, 8,000, 4,000, 210 is the black square. About 10. Now, that sounds pretty horrific. Like, okay, let's go home. It's all over. And why is it only 1 in 1,000? Well, the basic problem is buildings are mass-produced, but they're mass-produced idiosyncratically. They're mass-produced by different people, in every case, doing different things, or even worse, doing the same thing wrong the same way they've always done it. There is no integrated, industry-wide quality control, no organized continuous improvement. Continuous improvement depends on the individual businesses that either make the buildings or the components getting smarter and better as part of their market strategy. That is to say, better product would sell better. So we're counting on the competitive influence to improve buildings, okay? As opposed to, say, Boeing and theirs. And the other side of it is that 100,000 that I was showing you is just this year's crop, right? It doesn't even take that square, that's 2% of the existing building stock. So there's yet another bigger square that is 50 times larger than that blue square, which is all the buildings that are out there already. So if we go back to our same chart, now we start talking about body count. This year we're supposed to do 50% less, and we've got 200,000 buildings being built this year. And theoretically, if we were to meet the 2030 challenge, every single one of those would be 50% better than CBEX. Now, if they all met, as Ken pointed out, the 2004 code, in fact, they probably are. or quite close to it. But January, we're going to go to 60, and then we're going to be there for 5 years, which means over that 5 years, we're going to be doing 1 million more buildings, half of them new buildings and half of them renovations. Okay, about 500,000 new buildings and 500,000 total renovations of existing. Actually, that number is probably going to shift towards the renovations in this economy, and with the recognition that actually some of the best buildings we've got were built in the 20s and 30s, 40s, before we had a lot of energy to throw away. But as you look down through these, they're not decades. What's a half a decade? A demi-decade? These 5-year periods, what we see is we've got about 5 million buildings on the block here over the next 20 years. About 5 million buildings. That's if we don't increase our total building stock, which we probably will, but probably not by a huge amount. So that's the task that you people all need to solve for us as a nation, and that is we need 5 million new buildings that are much, much better than we're used to building. So you've got to come up with a solution. You have to come up with a solution. Nobody out there is going to come up with it. That's the thing that's a little disturbing. Most people kind of assume somebody else is going to fix this problem. Okay? No, it's going to happen a building at a time. Now, although 5 million sounds daunting, let's take a look at another infrastructure system that actually did exactly that. 1900, there were approximately 10 manufacturers of horseless carriages. There were no automobiles yet. They were just horseless carriages. And you can see why they were called that, because basically they would take the horse buggy, chop off the front, what did they call that thing? Tongue, thank you. And replace it with what was called a tiller, which was a stick that came up and you did this with it, like on a boat, like on a boat's rudder. And they'd throw a small engine behind the backside. But these horseless carriages, some of them had 4 horsepower. Now, in today's marketplace, that would sound absolutely ludicrous. But remember what they replaced. A single horse with 4 horsepower. We're talking monster machine here in 1901, right? Now, there were some interesting things going on at that time. By the way, this is not a field, contrary to popular belief, this is not a field in which the U.S. led. The late 1800s, the French had automobiles with steering wheels and fenders and 4 wheels and 4-wheel drive, but they weren't sold on this side of the pond because there weren't any roads or anything to use them on the way there was in Europe, or anywhere near the money that there was in Europe. By the way, those who say that we can't afford energy efficiency, these things sold for the same price as a house at that time. If you bought a car, you paid about the same amount you paid for a house. Not a big house, small house, but a house. Now, 1901, a guy named Olds came along, and he said, we got to get moving on this. What were the important elements? Well, there was the nickel-plated tiller, right? There was the lacquered body by Fisher with red and gold accents. And there was the same little 4-horsepower engine behind the seat, and this thing up front, which gave it its name, which was the curved dash Olds. This dashboard was designed to prevent the hooves of the horses from splattering you with mud, right? But there were no horses. But we still had the dashboard, even though we did not have fenders. And we didn't have brakes. But we did have a dashboard. So things were getting better. Now, what was important at this time was something else was going on that's very parallel to climate change. New York City. How much manure do you think they had to deal with in a year? Anybody want to estimate? Guesstimate? Anyone? How about 2.5 million pounds of manure? 2.5 million pounds. But that was only part of the story. There was also 60,000 gallons of horse urine. Okay, so there were some serious pollution problems. And that didn't count the 15,000 dead horses that had to be hauled off the streets, that died out there while they were working. Okay, so we have the horseless carriage moves along. Now we're up to, can you believe, 4,000 of these were sold by Olds. About 3,000 a year. I'm sorry, not 4,000, 12,000. About 3,000 a year for 4 years. What's even more ironic about this is that Olds was all set to expand their electric car business, which was built on the same chassis, but it had an electric motor and batteries, and cost a little more, but was the preferred car. That's what they were selling more of, until their factory burned down, which had all of the components for the electric cars. And they couldn't get replacement electric components. So they ended up building the gas engine model because that was the one that they had the parts for. Who knows what might have happened? Okay, 1908, the famous Model T. Okay, immediately, boom. Notice there's some nice changes that occurred in here. We do now have fenders. We do now have a steering wheel. We have a windshield instead of the curved mud catcher. By 1913, they were selling 100,000 units a year. 100,000 units a year. Remember, in 1900, they were selling in the tens of units. They're up to 100,000 a year, and by 1913, that was 1913, sorry, was 100,000. 1918 was 1 million. So, skyrocketing, and then of course, now we have 250 million of these things running around in this country right now. This is US only. So the lessons learned: appearance counts, price matters. And when I say price, one of the things, Ford was given credit for starting the assembly line. Actually, it was Olds. What Ford did was he motorized the assembly line so it would move by itself and pull things along. But what Ford also did, which is rarely mentioned, is that he overpaid his workers by somewhere in the neighborhood of about 40%, better than anybody else. And the reason he did it was, he said, if they don't earn enough, they can't buy my car. If they don't earn enough, they can't buy the car. And that's what drove the marketplace. And it also, of course, drove wages in other industries as his workers started to set the standard. Mass customization provides flexibility. If you buy a car today, you go into the dealer. If you're willing to be patient enough not to grab only the one that's on the lot, you can have any combination of accessories you want. They send it by electronic signal to the manufacturing plant. It goes into the computer, and your car is defined on the assembly line with the particular mix you wanted. So there can be thousands of variations of a car and still have the standardization that's so important. We've got to get there with buildings. We've got to get away from this. Every building is built brick by brick independently. We also need to get away from assuming that the building works, and we'll talk more about that. But what they found was the cars that made it were the cars that worked. The cars that didn't work disappeared. What do we do with buildings? We live in them anyway, right? We put up with them. My wife worked in an office where they had an open space underneath the office. It was a garage. And all winter long, Mondays were a killer because they turned the heat off on the weekend. The floor cooled, the concrete slab cooled, and it wasn't until about 2 o'clock on Monday that it was warm enough for people to take their coats off. Why would you put up with that? Why would you put up with it? Well, turned out because that office had a long-term lease with, my wife worked for the state. Okay, so do we have a parallel to the automobile? Well, I'm going to go out on a limb here and say LEED is kind of in that direction, but it's not really that direction. Not the same as the car in that it's not a product, but it is setting standards. And if we take LEED and we combine LEED with things like the codes Ken was talking about, and we look at utility incentives and federal incentives as drivers, and then we look at the public becoming more aware about energy costs, climate change, and sustainability, I think that mix is going to drive this renewal, this renaissance in buildings. Just as there's no one reason people buy cars, there's no one reason people build buildings. So we've got to have a broad approach and cover a lot of it. Now we're going to shift into the technical area a little bit here to look further at some of these issues. And we're going to start, I've got a number of hypothetical buildings thanks to Solarc, Mike Hatton and group in Eugene, Oregon. And they're not all the same buildings, so don't get confused by saying, well, that doesn't look like the previous one. What I've done is select slides that I hope illustrate a point rather than are consistently the same building over all of the slides. Okay, this in fact is a Boise building, and it's a code building, and it would come in at about 70,000 with the various exceptions and exemptions. And these are the different places you can see on the colored bars represent different elements that are making up the total energy. Yellow is lighting, green is miscellaneous, or plug load we'd call it normally. Red is space heat, blue is cooling, purple is fans and pumps, and the top ones are service hot water and exterior lighting, but they're relatively small elements.
So when you say 70,000, that corresponds to 70 CBEX index type numbers, kBTU?
kBTU, correct. 70 kBTU. And that's where we get into this issue of the codes, but that don't cover plug load, or they don't cover certain kinds of retail lighting, and et cetera. So this would be a starting point. And what we want to do is then to say, okay, well, this is where we are. What would it take to get us down to 50%, about 35? And then what would it take to get us down even further to under 20 so that we could reasonably expect to have renewable energy replace the remainder or offset the remainder of the energy that we do need? So that's kind of the question. And so here's a quiz. You all ready? Now, this I was saying I switched. I've switched to a laboratory because it's easier to demonstrate the problem. This is a constant volume reheat system, typical laboratory setup in Seattle. And this shows the energy use of different systems or different elements. And I took the names off to see if you could guess. What actually uses heat in the building? What do you think the big one is? Now this is, I realize you're not all engineers, and so you can't lose. You're not going to get yelled at for getting the wrong answer. Cool. This is heating. We're talking about heating energy here only. Where does the heat go? What do you think it's doing?
Air.
Heating air. Okay. Probably. Well, I'm going to make this a painless death. The biggest use of heat, in labs at least, is reheat. What does that mean? Well, what it means is you bring air in and you cool it down to what you need for the coolest part of the lab, and then you reheat it for all of the less cool parts that don't need that cooling. You take that cold air and put the heat back in. So you've taken air, let's say at 70 degrees, and cooled it to 55, and then you put heat back in to get it back up to, say, 60 or something. And that process is called reheating, and it is one of the most common problems in air systems because you don't have the same heat loads throughout the building. So the level of discrimination that you can make between spaces, i.e. how many zones you have that are fed, determines how much you can independently target the cooling and heating needs of each space. So the biggest number in the case of labs is reheat, which effectively means that you're doubling up on your energy because you're first cooling and then you're putting the heat back in. The second largest is a tie between oversizing and windows. Oversizing and windows. What's oversizing? That's fear of the insurance policy, right? Or the lawyers, or both. And so we have a national phobia about making sure there's always enough, because otherwise we might get hit with a lawsuit. And that costs. That's not free. That costs quite a bit. Notice that the envelope, windows, doors, walls, and roof, they use almost no heat. They're only a tiny fraction, they're less than 20% of the total. Okay, same quiz, this time on the cooling side. And the same issue. Where is all this cooling going? And I won't bore you with the weight because there's no real reason that you would know the answers to these questions. Okay, now this actually looks a little better in that, well, it doesn't look better in terms of, I got to remember not to point. Doesn't look better in terms of what's the biggest use. The biggest use for cooling is even more egregious than it was in heating, and that is oversizing the cooling system. That's the biggest inefficiency in most buildings. Second biggest is actually dealing with air, dealing with ventilation. Now there's a real use. You're actually doing something constructive there. The third highest, I'm trying to get my mouse to work here, is lighting. Okay? Now, fan heat is interesting because fan heat is essentially the energy that's being used by the system that distributes the cooling. So it's part of the cooling is cooling the system that's making the cooling. Right? And so the bigger that system is, the more you're going to have in this category. And then reheat here isn't as big, primarily because you're not extra cooling. What you're doing is you're cooling as close as you can and then reheating what you don't need. And so that's why it's not as big an issue as it is on the heating side. But I can tell you this, in as you probably know, New Buildings Institute did a study of LEED buildings to see if they really saved energy, and one of the answers was, well, yeah, they do. But when we looked at the buildings that didn't save much or were in the lower part of the category, almost without fail, there was a huge amount of this simultaneous heating and cooling going on, the reheat going on, where they would cool it, heat it, cool it, heat it, cool it, heat it. And that waste is enormous in many buildings.
Does oversize imply that as you go to a larger cooling unit, your overall efficiency drops?
Yes. The short answer is yes, because when you oversize, you basically, the optimum operating point for that equipment is higher than you need. So you never get there. There's another, I don't think it's a dirty little secret, I think everybody knows it. The reality is that most buildings, most of the time, are only using a tiny fraction of those systems anyway. The normal operating level, you don't have 20 below zero days, 100 days a year. I mean, even in Boise, I mean, you guys have colder weather than we do in Portland, but what is it, maybe a dozen days that are down in the, you know, -10, -20? I don't know. What is it? 0 days. Okay. It's not as cold as I thought it was here. The point is that you're not doing that much of the time. Most of the time, you're only heating a little bit. Most of the time, you're only cooling a little bit. But we build the equipment as if it's got to handle the whole shooting match. Now, this is a Terry Egner statement. This is not a Better Brick statement, and this is not an NBI statement. And I'm not even sure if the lab here would be interested in standing behind this one. But I'm going to predict that VAV is going to disappear within 10 years as the basic mainstream system for new buildings. Those of you who have as much gray hair as I do, I used to be 6'4", and I had a yeah. In 1974, 73, 74, we had the first oil embargo, and in 1978 we had the second oil embargo, and both of those kicked energy prices sky high. As a result, everybody suddenly said we can't afford to run our buildings the way we have because the energy costs are way too high, much too expensive. And up until that time, the most common system was what was called a dual duct constant volume system. And it had hot air going down one tube and cold air down another, and then you just blended them to get the temperature you wanted. It was magnificent in terms of comfort. It was horrible in terms of energy use because you were taking 65-degree air, splitting it, heating half of it to 80, the other half down to 50, and then bringing it together to get 65-degree air, which is what you had to start with, right? That's what was happening in a lot of the time. Okay, well, here we have the same problem, except what VAV did was it got rid of a lot of that constant mixing. And it went to one duct, typically, with the reheat option at the far end. So if it was too cold, you could warm it back up a little. The problem is not the mechanism. The problem is that you're using air to move energy. You're using air to move energy, and air has two lousy properties. One is it doesn't hold energy. So you have to use a huge amount of air to move any amount at all. The second is that it's compressible, which means that if a fan starts spinning, the air doesn't start moving right away. It has to build momentum and be compressed and start moving. Whereas if it were liquid like water, the minute the pump spins, full volume is going. That's because water is not compressible, whereas air is compressible. So you lose on multiple accounts. So I think it's going to go away, and it's going to get replaced with a number of other things we'll talk about quickly. Okay, jumping back, we're looking for ways in which to improve our systems. You don't need to try and read the details. Basically, what you would do on an engineering/architectural basis, and you need to both be involved because it impacts both the shell and the systems, is you do things like improve insulation levels, get higher quality lighting, automatic daylighting controls, pre-tempering, recycling, and heat recovery, and that last bar over there is get rid of all of the extra system you never needed in the first place because you oversized it. Okay? If you do those things, you can gradually, each one of them reduces it, and just doing what we were looking at there can get us down into the range of below 30,000, just above 30,000. In other words, this level here, where we're looking at systems, and now we can meet the 50 challenge anyway. We're right on the edge of the 60. And then this last one is if you then use some solar, some renewables, you can go further. This is not PVs, this is solar thermal. You can get further down. So we now know right now, with no magic, no tricks, we can get these numbers down to some approximation of the immediate 2030 challenge. What will happen with VAV? Well, to do this, you've got to change the kinds of systems you have, but I can't point there, I'm sorry. There's something, and you'll just have to take my word on this if you're not an engineer. Different kinds of systems work better at certain capacities. Certain things do not have the ability to deal with high capacity. The most obvious of which is the bottom one here, natural ventilation. You cannot use natural ventilation in an energy-dense setting to take away the heat, because you'd have to have a tornado going in order to have enough air move through to carry the heat away. So that's an example. Well, each of these, as we go up from the bottom, indirect evaporative cooling, it's limited partly by airflow and by the availability of air to absorb moisture and cool. Natural ventilation with thermal mass, we can get a little better because we can use night cooling when nobody's there and move a lot of air through. Radiant cooling is limited by the laws of radiation. There's only so much energy that can be transferred via radiation. So what this means is that some of the things that we like to look for, because they're also low energy users in terms of their system cost, don't have a lot of muscle. They don't have the ability to handle high density loads. Well, the solution is not, which it has been in the past, to go to a high volume solution. In other words, brute force our way to a temperature that's livable. The solution is to get rid of those loads and get them down to a level where these simpler, less energy intensive solutions can work. So if we look up the top, there are two red dots there. The one on the right is where the system, this building in Boise was when we started, and the larger one in the center is where it could be taken down to just by those straightforward energy efficiency measures that we had talked about. And by doing that, we move ourselves from saying, okay, here, there's only one solution, VAV. Here, we have a number of things that can do the same job. We've got displacement ventilation, radiant cooling, and natural ventilation with thermal mass. All can meet the need, because it's now a much smaller need. So the first rule of heading to net zero is get rid of the excess waste. Cut your load. Cut your load. Okay, what are good candidates for this kind of stuff? And this is Yogi Berra's statement. I back him up 100%. Some of the technologies. This came from NBI's study. These were the, sorry, I get caught with this. Starting at the top and going down, this number represents the percent of buildings that had that technology in it. And what you can see is that daylighting and controls and increased insulation were very much the sorts of things that people were using to get to, and these are buildings that were getting to 50% savings. HVAC efficiency, down at the bottom we're seeing things like ground source heat pump and VFDs. Well, that's changing. That's changing rapidly. When we looked at the best and worst of LEED recently, the top buildings, 8 out of 10 of them were ground source heat pumps. 8 out of 10 were ground source heat pumps of the best buildings. So the technology is beginning to change as we start looking further down the list, as it were. Ground source heat pumps, variable refrigerant flow, VRF systems, which are kind of like a split system where you've got a thing outside and a thing inside, but they are able to handle multiple spaces, multiple temperatures. Condensing boilers. Many of these things, by the way, weren't even around 10 or 15 years ago. These are new. This is, remember, when we started making cars, there were no fenders, right? There were no fenders. And when we were and we didn't have steering wheels, we had tillers. That only lasted for 2 years before we got smart enough to put a steering wheel on. We're learning, and that learning is going to come about because you people are going to check this stuff out and you're going to work on it. Energy recovery, chilled beams, radiant surface, evaporative cooling, all the stuff we were talking about. You can't get where we're talking about if you don't use the daylight. If you require electric lighting for all of your load, you're going to be in trouble. You've got to take advantage of daylighting. You have to, where possible, we recommend hybrid systems, natural ventilation, where it works, as long as it works, and then backed up by a modest conventional system for the days when natural doesn't work. I can't underemphasize the necessity for a tight shell. And for much of the country, not all of it, but for much of the US, mass is a major advantage. You don't have to think too hard about this. We lived in caves for centuries, for millennia, for a very good reason. They're high mass, and the temperature stays even. You know, take a look at the Spanish mission architecture. Works in the desert. Why is that? Mass. Okay, night venting is tied in with that. What are some other things? Anybody here have a favorite technology they think is going to take off and help a lot? Nobody?
Sweaters.
Sweaters. Now, we can't do that. Politically, it's the death knell. We now know that from Carter. But your point is well taken. No, it is, and we'll come back to that.
I've been thinking an electric heated jacket I use for motorcycling.
Okay, so maybe you're not, maybe I shouldn't have jumped so quickly again at the sweaters. How many of you know the novel Dune? Not too many people. Interesting. You should get this book. It's fantastic. D-U-N-E, like sand dune. Dune. It's about this planet. And everybody wears their still suit, it's called. Still as in like making liquor. And what it does, it traps all the moisture, and it has the heater and the cooler, and everything's built in. Why cool and heat the buildings if all the people are already taken care of? So maybe, okay. Other things that you think that may go, so personal clothing choices. This we'll come back to in a few minutes for another reason. Okay. This is a list of technologies that was done in 2002, so it's quite out of date now. But it still was amazing in terms of, these are the technically available stuff and how fast it pays back. Notice that chill beams have a payback of 0. Chill beams have they are cost effective right out of the box. How many chill beam projects have you seen? Only a couple. Dedicated outdoor air systems. Cost effective right out of the box. That's something I'm beginning to see more of, but it's still fairly rare. In other words, if you separate the outdoor air system from air moving for heating and cooling, for conditioning, it's a much smaller volume. And so you have much less energy tied up in tempering the outside air if it's for breathing than you do if you're trying to move heat and cool around with it. Bunch of different things here. One of the improved duct sealing is way out there at 10 years. I was a little surprised because I've heard that duct is supposed to save quite a bit. And it does in one sense, but in another sense, if you built the house right, the ducts wouldn't be outside, they'd be inside. And therefore, the losses wouldn't be losses, except fan losses. Okay, we need to shift gears if we're going to make this thing work. We can't keep going building the same way we've been building. We need what's known as a paradigm shift, is the famous phrase everybody used for years. And I want to point out to you that a Hummer will not evolve into a Prius. We've got to make the change. Okay, it doesn't do it on its own. Although I did notice, how many of you have noticed that Hummers do devolve? That is to say, they started out this big, and the next year they were this big, and the next year they were this big, and now they're not much bigger than a Jeep. But when they first started out, they took 2.5 lanes. Okay, new acronym, DOT. Designers, operators, tenants. If we're going to make this work, it's not going to be because you came up with a brilliant idea, it was executed, and therefore it's solved. Whether you're the architect or the operator or the tenant, you're all going to have to play, if we're really going to talk about numbers that are as low as 20 kilobTUs per square foot. Because that's less than most places are using for cooling right now alone. And it's less than many are using for lighting alone. And it has to do cooling, lighting, heating, plug load at less energy than you're using for any one of those right now. Okay, how are we going to do that? For those of you who haven't seen this yet, I'll just leave it up there for another second. This is Charlie Brown's, G.Z. Brown, University of Oregon, School of Architecture. His concept, I have a simplified version of it that makes it easier to work with if you don't have a book in front of you. And that is, when we look at buildings, we really don't have, many people mix and match. They mix up the system with the load creators. And that is that we have climate, it's cold outside, it's hot outside, building use, the program, what are you doing in there, and the site and building design. Those define what the loads are that the systems need to resolve. And the systems are the heating, the cooling, and the lighting. Now, the lighting is also a load as part of the cooling system. And so it's a little mixed. But basically, you have this two-way, we have this division of things between the climate load, the climate building use and site producing the load, and the system meeting the load. And what we need to be doing here to get to these net zero buildings is we need that the energy from the energy we're going to use for these systems has to come from renewables. Okay? Now, the conventional efficient design, what you do is you have your loads on the left, and they create a system requirement. How big is your chiller or boiler? And if you're efficient, what you do is you say, hey, I can put in an efficient boiler. Instead of a conventional boiler, I'm going to put in a condensing boiler, and I'm going to save 15%. Or instead of an air-cooled recip chiller, I'm going to put in a water-cooled centrifugal chiller that has super recovery everything on it, high efficiency. And by doing that, what you do is by putting efficient systems in, you reduce the amount of energy you use. This is the model that for the utility incentive. If you use a more efficient widget, we'll give you credit for the energy you're saving with an incentive. Now, there's nothing wrong with this model. It's only incomplete. It doesn't deal with the whole problem because the systems are interrelated. So here's the way you do it when you do integrated design. And this is why you need your engineer involved, not at the 95% design stage, but at the 5% design stage. The first thing you do is you get rid of as many loads as you can. And you do that by things like orientation and selection of glazing and all of those kinds of things, lining it up so that you have airflows. And you reduce those loads. You choose smart lighting so that you're not wasting a lot of energy cooling for lights you didn't need. So the first thing you do is you make small loads. Small loads require smaller systems. So you've got a savings because the system's smaller and the energy it uses is smaller. But then the smart move is, okay, for those systems, let's do what we did the first time, and that is buy better equipment. And since it's smaller, our budget may not change. In fact, that's what we're seeing now regularly, is that the smart energy-saving building is coming in for the same price as the dumb, wasteful building because it's smaller and you can take that extra money and put it into higher quality instead of bigger size. And so this is the integrated design that has to happen. Some examples. Mount Angel Abbey, if you ever get a chance to visit, it's in the Willamette Valley there. Brilliant piece of work by Charlie Brown and Heinz Rudolph from Bora. They mocked this thing up. They squeezed every ounce of energy they could out of it. The basic concept is have a large skylight that is adequate so you have no electric light requirement during the school day. And then that very elaborate piece of what looks like artwork is in fact movable louvers that operate to direct the lighting where you want it, when you want it. The nice thing is, look at the EUI. Now you know what an EUI is. Oh, I know you don't, because I never told you that. Kilobitu's per square foot per year is also called the Energy Use Index for the building, or the EUI. So it's like when we say, what do we call it? What do we call the mileage rating? EPA. What's the EPA rating on a car? And somebody says, oh, it's 22 in town and 24 on the highway. You know right away they're talking about miles per gallon, right? Well, if you see an EUI, what they're talking about is kilobtu's per square foot per year. Is 19 good, medium, or bad? Thumbs, let's see them. It's great. It's like 60 to 70% better than typical. Okay, better than recent code. Costs 5% more than the conventional building. 5% more to save 60% on energy use. And have a nicer space, by the way. I think they're gorgeous buildings. National Energy Lab. EUI 31. Where are the thumbs? Okay, mix of up and medium. Good. There's some people who are getting more, you're becoming connoisseurs of energy value and where they ought to be. Well, it's a national lab, so we'll give them a little slack, okay? The other thing that's important about this building is that this is one of the few buildings that's big. This is a big building. It's 280,000 square feet. It's 4 stories on one side, 3 on the other. A lot of buildings that are very energy efficient are very small. And so they can be energy efficient. You know, a little one-room cabin works really well with about a candle worth of energy. But you get to these guys and you've got some problems with open office and that sort of thing. They solved most of them, got down to 31. Richardsville Elementary, EUI 17. Okay, it's back up there again. This is on the same level as Charlie's. Okay, they used a different model here. They built a large building. This is 500 students. It's a large, solid, rectangular building, 2 stories. Why 2 stories? I'll give you a hint. Oops, if I don't kill myself first. People who, can they see that? Can you show them this on the screen? Why 2 stories? We can get sunlight to every classroom on 2 stories because the top story you can use skylights and side windows. On the lower you can use sonotubes, solar tubes, and side lights. So daylighting for both of those buildings, daylighting eliminates, I'm going to repeat that word, eliminates the need for lighting the vast majority of the time the school is in session. So there goes that whole chunk of energy, and with it goes the whole chunk of cooling needed to get rid of the heat from the lights. Now, there is a little negative, and that is if you're in a cold climate, you may be counting on the lights to keep you warm. But that's okay, because it isn't going to cost as much for a gas heat as it does for electric lights. Electricity is about 3 times as expensive on a carbon basis.
So is that the modeled number, or is that the actual measured number?
I'm glad you asked that. Performance, this is real. This one's real. Unfortunately, I can't say that about the national labs. That was still a modeled number. They hadn't had a whole year of running it yet.
Terry, where is it?
Which?
Where is this one?
This one's in Kentucky. What do they call that place?
That's close enough.
Okay. It's Bowling Green. Thank you.
I do not speak your language well. What is conversion between BTU and kilowatt hour?
BTU, let's see, you got one kilowatt hour. 1 kilowatt hour is 3,413 BTUs.
Thank you.
Okay, or 1 BTU, I mean 1 watt is 3.413, thousandths of a kilowatt hour. Yeah. Okay, so this is 17. Packard office building, California. I can't remember exactly where that is. Delray, someplace like that. 17. Office. What do we got? Okay. A little easier climate, perhaps, than some to deal with. It's drier and sunnier. But what they did here was they took the office and they split it They essentially took the building and divided it in two. Why would they do that? Daylighting, exactly. Gives you double-loaded sides that both can have windows. No space in the building is more than 20 feet away from a window. Bingo. There goes a whole chunk of your lighting load. This is a real number. This is not a model number. Okay, now, all that said, what we do know from the study that was done by NBI is that buildings don't always end up operating the way that they were designed, or maybe not built the way they were designed. And that is, when we looked at a lot of these, for instance, the worst two buildings, the worst building, we called them up and said, there must be a mistake with the metered data you sent us because it doesn't fit your building at all. It's crazy. I mean, it's like 3 times what you should be using. And they said, oh. And they went back and they said, no, that was our data. 2 weeks later, miraculously, the buildings used about half as much energy. Nobody knows why, or nobody will say why, I should say. Nobody who's worried about lawsuits will claim the reason. But whatever it was, they fixed half of it overnight. The second building that was in that same category turned out that the controls contractor went bankrupt just as he finished the project, didn't bother to install any software. Everything was on auto. Simple auto. On, and on. Okay? And again, what they've done is that, so what we're looking at here is that operations can have a huge impact. I have a friend, Phil Irmer, who's the facility manager down at HP. And this is the kind of stuff they make to give you a sense of the kind of place it is. It's a combination of office and basically labs. They have, as you would expect, an exotic fan system. Guess what happened? Why do you think there are 2 of them? Redundancy, because this is a clean lab, and man, if one of those goes down, how many dollars do you think they lose if they didn't have a backup? Okay, when the last time, by the way, this thing weighs 480 pounds is the spinner, and 2,800 pounds for the motor. Now, the reason he put that information in it is you don't pick this up and set it aside and put another one in. You bring in the crane and pick this one up, okay? Well, he has been encouraged by his management to look for next generation solutions to problems when they need to fix something. Don't replace something automatically with what was there before. See if there's a better version now. And what he did was he looked at fan walls. And a fan wall is, instead of one giant fan, you have a dozen or 16, I think, no, 12 in this case. No, 15. No, yeah, 15. 15 small fans, all pushing air instead of one big fan pushing air. And it turns out, oddly enough, thanks to fan laws, that this actually uses less energy than the big fan did. So he took a look at that, and he looked at the cost. Standard replacement's $170,000. The fan wall's $188,000. It's going to cost him $17,000 more, but the state was willing to give them an incentive because of the efficiency of $14,000. So it ended up with a $3,000 difference in cost between the fan wall and the old style fan. Okay, let's look at the energy use. $22,000 for a standard fan versus $16,000 for a fan wall. So they every year would get $6,000 back off of the fan wall. Is this beginning to look like a no-brainer? You start to throw in the incentive of $14,000 and it's a half-year payback. Now note that if the state had not given them any incentive at all, it would have been less than 3-year payback. Less than a 3-year payback. So he has now moved HP to a new level in terms of efficiency and in terms of the technologies to embrace. They now understand that fan walls are there and they work. This is the steering wheel right? You put a steering wheel on after you've had a tiller for all of your life, and oh man, I'm never going back to that tiller, right? The steering wheel is too good an answer. This is what's going to happen, and you're going to drive it. We are going to find the products that work, and we're going to make these buildings more efficient, and it's going to happen because everybody is doing, not just the designers, but the operators as well. By the way, there are a few other things. You got redundancy because if one of those little fans went out, it wasn't a big deal. They had a spare anyway. And a technician can change one of those little fans if it goes out, literally by going, picking it up, taking it, and putting a new one in. No crane, right? No special rigging. It's smaller footprint, and it reduced their electrical infrastructure costs for wiring because it's lower load. This is his new projects. I'm not even going to leave it up there long enough, but that's the thinking that's going on at HP. Progress means looking forward for better answers, not looking backwards to the old solutions. Now, the last group, it comes into this gentleman's comment of the sweater as a solution. Tenants drive probably close to 30% of the energy use in the building by their behavior. That's my number. I just made it up. Okay, but I think you'll find that it's not far off. Let's look internationally at what people think about energy use. My favorite is, well, let's look down. Here's ASHRAE's comfort zone. Here's the expanded comfort zone that ASHRAE allows if you don't have mechanical cooling, if you use natural ventilation or other means. They'll allow it. And that is because the occupants have to be able to control the cooling. Those are the two requirements for the expanded. This is the Washington Energy Code. Here's France. France is kind of like ASHRAE, except they don't mind getting cold, right? So they go all the way down here to 65, no prob. Why? Because they wear sweaters. Germany's kind of tight about this stuff. They're closer to the US. United Kingdom, I love this. This is just so stiff upper lip. Higher temperatures allowed for less than 10 days a year. So you can go beyond 83, but not more than 10 days. But there's no real upper limit. And then high performance classroom in the US, this is the level, but you have to have ceiling fans if you get to the upper end. So what this is telling us is that occupants' expectations have a lot of impact on how we perceive whether we're comfortable or not. And if we're told that we can't control it, our response typically is, well, damn it, then it better be 72 degrees all the time. If you're not going to let me control any of it, then you better meet your responsibility to keep me comfortable. Whereas if you say, hey, you run it the way you want, people start coming in shorts and opening the windows and saying, God, this is great, this spring air, I love it. Right? And the temperature goes up part of the day and down. This is called seasonal adjusted comfort. We now have actual studies that have shown that people behave rationally in terms of climate. If it gets hot, they wear lighter clothes. If it gets cold, they wear heavier clothes. If they know that they're responsible for the temperature. If they know that they're going to be the ones setting the temperature in the office. You don't wear three-piece wool suits in August. Not too hard to figure out. The other thing that bothers people is lighting. Here's the occupant design criteria. Here's IES, that's us. And then France and Austria and Germany. Very low, and it's kind of like, hey, not our problem. Because these are the design requirements. Doesn't mean that you can't have good lights. What it means is that it's not the building designer's problem, it's the occupant's problem. A very different concept from what we have here. Finally, plug load. And this picture means nothing. But it was colorful, so I really liked it and I wanted to put it in there. This is a map. This is a map of energy use on a daily basis. Each of these vertical lines is a day. And what you do is if you map energy use in a space, you'll see this standard pattern emerging, And then you can spot when things go wrong very quickly, which is what's showing there. And that's basically, we use this a lot for tracking plug loads, and the reason we do it is that plug loads are the wild cards. You know when the heater's on, you know when the chiller's on, you've got lots of data on that. What you don't know is when people are turning stuff on at their desk, turning stuff off, unplugging, plugging, taking it home. Electric heaters, it's always interesting to do a study of an office building and find out how much heating they have, and then discover that about 10% of their electric load is heaters underneath the desks that nobody talks about, but they're actually driving the temperature. Okay, so if we're going to make this work, what we've got to do is we've got to bring these three groups together as part of the design scenario. We need to not have designers operating in isolation, and particularly not just architects operating in isolation, but architects, engineers, bring in the building operator, bring in tenants, find out what people think will work, and get a buy-in early, because if you really want those low numbers, you're going to have cooperative tenants who are saying, yes, we think it's right to do that, and we're willing to do our share, which may mean wearing a sweater. Okay? So that's the end of my presentation, and I still have 3 minutes. Pretty good. Ken's been helping me with sort of timeout signals and in the back of the room to keep me on track here. Questions?
You haven't said anything about differing climates, and it seems like this theory works differently, say, in our climate here than in Georgia.
Absolutely. Absolutely. And for instance, one of the things here is we can use economizers. Use outside air for free, a huge portion of the year. Seattle, it's like 85% if you do your systems well, your loads low. You can't do that in the Southeast, in Atlanta. But what we do have that works in Atlanta is heat reclaim combined with dehumidification, not refrigeration dehumidification, but using dehumidification wheels as part of the heat recovery, or in this case, actually in Atlanta, the cool recovery, the coolth recovered in the heat exchangers. So you're absolutely right on. There's a different answer for every climate.
So that's like you're exhausting temperate air that's been dehumidified, and you're putting humidity into it as it leaves the building and dehumidifying.
That's exactly it. Yeah, you keep dumping the humidity out. Plus, you've got humidity in the building being generated by all those protoplasmic carbon-based critters running around, the people, right? So you've got to dump that as well. But that's absolutely, it's not, and it's interesting, the heating, refrigeration, air conditioning industry today announced that, hey, maybe we should have different equipment for different climate zones in this country instead of what they have insisted on up until now, which is a single standard for the entire country. And they're now saying, yes, we'll accept a climate by climate zone definition of that. So that's great progress, and you're absolutely correct. We've got different answers for different, not just climates, but kinds of buildings, uses, all sorts of microclimate issues too. Other questions? Sure.
So I mentioned this earlier. It seems like when we're doing our buildings, we're often at around 30% below ash rate on our energy modeling. And it looks to me like on your chart with the CBEX index, that's about, 25% of CBEX. So that's much better than I was thinking we were doing. Is that a reasonable conclusion?
No. Yes and no. And it really depends on how the modeling is being done. The problem with 90.1 is that it generally does not include plug load. And so there's this wild card. It's like lighting budgets. You could say lighting is restricted to 1 watt per square foot or something. Okay? And they accept that it doesn't count retail lighting. And it doesn't count desktop lighting. And it doesn't count, and there's a whole long list of it doesn't counts. That's why, as somebody had said, was that number real or modeled is so critical. We're not going to get where we need to go unless we do the same thing we do with cars. We put speedometers and odometers on them. and we actually measure the energy going in and say, hey, you know, this actually did get 17. It didn't claim 17 and get 42. So that's going to be critical. And the modeling is also being improved, by the way. We're getting better at that, but it's an issue.
So because of time, I think what we'll do is end the session here, and if you want to hang out and talk to Terry and ask questions, he's going to be here, and thanks for a great presentation, Terry.
My pleasure.